Welcome to AUV Hydrodynamic Design Fundamentals. When designing an autonomous underwater vehicle, understanding fluid dynamics is absolutely crucial for mission success. The key principle we need to master is drag minimization while maintaining structural integrity. Think of an AUV as a submarine that needs to move efficiently through water, which is 800 times denser than air. The hull shape directly determines how much energy we need to propel the vehicle. A streamlined torpedo configuration with a length-to-diameter ratio of 7:1 provides the optimal balance. This means if our AUV has a diameter of 20 centimeters, the ideal length would be 1.4 meters. The drag force calculation uses the formula drag equals 1/2 times water density times velocity squared times drag coefficient times frontal area. For seawater at 1,025 kilograms per cubic meter, even small improvements in drag coefficient can dramatically reduce power consumption. Now let's explore the practical implications of these calculations. When we calculate buoyancy control, we must ensure our AUV achieves neutral buoyancy at its operational depth. This is where precision becomes critical. The buoyancy force equals the density of seawater times gravitational acceleration times the volume of water displaced. However, as the AUV descends, water pressure increases, slightly compressing the hull and changing the displaced volume. At 100 meters depth, pressure increases to 11 atmospheres, requiring careful compensation calculations. The control system must continuously adjust ballast or variable buoyancy chambers to maintain neutral buoyancy. This dynamic balance allows the AUV to hover, ascend, or descend with minimal energy expenditure. Engineers must also account for payload weight changes during the mission, such as when scientific samples are collected or when battery weight decreases as power is consumed. These calculations form the foundation for all subsequent propulsion and control system designs.